Hello everyone, my name is Bappi Hamed and welcome to this video. So guys, in this video onward, I'll be talking about different runtime complexities. So there are many runtime complexities in an algorithm, but I'll be talking about most used runtime complexities in this series. So guys, here if you see, here are some list of the runtime complexities, okay, present in an algorithm, and these are like most used runtime complexities. So in this video, I'm going to discuss about constant runtime complexity and linear runtime complexity. So first of all, let's try to see what is constant runtime complexity. So guys, here if you see, we usually represent this constant runtime complexity with the help of order of 1. Always try to remember in constant runtime complexity, given any kinds of input, execution time will remain same. So let's try to understand this part with the help of this function. So guys, here if you see, this function returns multiplication of the number. So this function will return the multiplication of the same number, as you can see, n multiplied by n. So let's say as an input actually we're giving 3 here, so it will return you 3 multiplied by 3, which is nothing but 9. Okay. So this is the function actually, and here if you see, here only one operation is happening, which is nothing but the multiplication. Okay. So here if you give 3 or let's say 3 million, the execution time will remain same here because only one operation is happening here. Okay. So let's try to code this function, okay, on our code editor and try to understand what I'm trying to say. So guys, I'm in my neural lab. So here what I will do, I will just create one folder here. So let me create one folder and I will just name it, name this folder name as Big O. Okay, so let's name it as Big O. So inside Big O, I'll create one file. So let me just redirect to this folder, cd Big O. Okay, now inside that, I'm going to create one file and I'll just name it as constant, because this is the constant runtime complexity we are discussing. So constant.py. So here I have created. Now just let me write down the same function I showed you. So def multiply numbers. Okay, so this will take one input called n, any kinds of number, and it will return n multiplied by n. Okay, now let me just call this function here. So here I will get my results, then I will call this function, and here as an input, let's first of all give 3 here. Okay, I'll give 3 here and I'll just try to print these results, print my results. Okay, now if I execute this particular function, if you see, if I just write python constant.py, see, it will return me 9. But let's say instead of giving 3, if I give 3000 also, so the execution time will remain same. As you can see, execution time will remain same because here only one operation is happening, which is nothing but multiplication. Okay, so that is why we call it as constant runtime complexities. So always try to remember in constant runtime complexities, given any kinds of input, execution time will remain same. Okay, so if you let's say give here let's say 30,000 also, so the execution time will remain same. Okay, so that's called actually constant runtime complexity. Now let me give you one real-time example of this constant runtime complexities. So let's say you have set of cards. Okay, now I told you just pick up any random card from this list of card. Okay, now what you will do, you'll just randomly pick up one particular card. So let's say this is the card you have picked up. Okay, so this is the random card. So in this case actually the time actually you have taken, which is nothing but the constant time. Okay, but let's say if I tell you just try to figure out number 8 card from this list, then what you need to do, you need to find that 8 from this list of the card. Okay, and it will take some couple of time, okay, from you. And once you will get that 8 card from this list of the card, you will return me. Okay, so in this case actually this won't be constant time complexity. Okay, so that is why we always represent this constant time complexity with the help of this order of 1. Okay, so here is another example. As you can see, so let's say you have one array here. Okay, so in this array actually you have some number 1 2 3 4 5. Now if I tell you just pick up the first element of this array, now what you will do, you will just write the index, okay, index number of that array. Let's say 0 is present at the index 0. So if you write like that, okay, it will return you the first elements of this array. Okay, now here if you see, it takes constant time to access the first elements. Okay, because here you are not looking for the specific number. Okay, you know, like you need to access the first element from this array. Okay, so that is why we call it as constant runtime complexity. Now, if you plot this constant runtime complexity on a graph, going forward, I will do the comparison between different runtime complexities. Then you will see the final graph, like how it will look like. But in this case, here if you see, this is the individual constant runtime complexity graph. So here if you see, you have like number of data, that means volume of data. and here is the execution time. Okay, if your number of data is increasing, there is no issue with that. Okay, the execution time will remain same. That would be completely constant. Okay, so this is the graph of this constant runtime complexities. So guys, I hope you got this constant runtime complexities. Now let's try to understand these linear runtime complexities. So guys, here if you see, this is the linear runtime complexities. So we usually define these linear runtime complexities with the help of this order of n. So here your runtime increases based on the input data you'll be giving. So here runtime complexity will grow in the direct proportion of the input data you will be giving. So to give you this example, here I kept another function. As you can see, this is the function. So basically it prints the item. So here if you see, this function takes one parameter called n, and it is looping through that particular number and it is printing the numbers one by one. Okay, so this is the function I have written here. Now let's try to write this function on the code editor and try to understand this linear runtime complexities. So here what I will do, I will clear the terminal, and again I will be creating another file here inside BigO, and I will just name it as linear. Okay, linear.py, because this is the linear runtime complexity I'm going to discuss. Now here, let me write down the function. So print item. Okay, so this will take one input called n. Then I will just loop through this input. So I'll just write for I in range. So here I will give the n. Then it will print that particular number one by one as a sequence. Now here I'll just call this function print print items, and here I will give, let's say, 10. Okay, so it will actually print 0 to 9. Okay, 0 to 9, because here I have given 10. So it will first of all get all the numbers 0 to 9, that means 10, and it will print all the number here. So now if I execute this particular code here, so linear.py, now here if you see, it has print 0 to 9, that means 10 number. Okay, now I think I don't need to give print here because I already given the print statement here. I think I can execute like that only. Yeah, so see, it is printing 0 to 9. Now let's say if I give 100 here, so it will print 0 to 100. Now see, execution time will increase because I have increased my input size here. Okay, now see, execution time will increase. So you can't actually observe here actually like in a very good way, because this is like very small number. Okay, so actually that's why you can't actually observe it is taking like how much time. But if you increase this number, okay, if you increase this number up more, you will observe this time will increase. See, this time will increase. Okay, now if I, let's say, reduce this number, let's say if I give 5 here, if you see here, it will print 5 times. Okay, now this execution time will be a little bit less. Okay, so that is why we call it as linear runtime complexity. So basically if we increase the input data here, okay, if we increase the input data here, if you see, number of operation is also increasing. Okay, it is. So let's say if I have given 10 here, so here 10 time operation is happening. Okay, 10 time it is printing. Okay, if you see here, it is printing 10 time. Okay, but whenever I'm reducing the number, also operation is also reducing. Okay, here if you see, it is printing 5 time. So that is why we call it as linear runtime complexities. Okay, so that is why linear runtime is always proportional to your input size. Okay, the input size you will be giving based on that. So the input size you will be giving based on that, your runtime will increase and decrease. Got it? Now guys, let's take the same card example and try to understand this linear runtime complexities. So as you can see, this is the same example I have showed you for the constant as well. So here, let's say you have list of the card, and if I tell you just figure out this 10 number of card from this particular list. So what you need to do, you need to manually figure it out. So once you get it, okay, you will check one by one, and once you get it, you will return me that particular card. But let's say here you have lots of card. Okay, definitely it will take lots of time for you to figure out this particular card. But here if you are having less card, so definitely it will take less time from you to figure out this particular card. Okay, so that means if your number of data is increasing, your number of operation is also increasing. Okay, that means runtime is also increasing. Okay, and if it is decreasing, that means everything is decreasing in this case. Okay, and that is why we call it as linear runtime complexities, and it is defined as order of n. Okay, we usually call it as order of n. Now if you see this example, actually this array example here, if you see, now here if I tell you just try to print all the element present in this array, now what you need to do, you will be using one for loop, and with the help of this for loop you will be printing all of them. Now let's see if this array size is increasing. Definitely I mean number of operation will also increasing, okay, because it will print all the numbers present in this list, then it will give you that particular number, okay. And if I'm talking about like how to represent this linear runtime complexities in a graph, okay, so here is the graph. Actually you can see that means if your size of input is increasing, that means your time is also increasing, okay. And this is the linear, okay, this is the linear line you can see. So that's why we call it as linear runtime complexities. So yes guys, this is all about our constant and linear runtime complexities, okay. In our next video, I will show you some more runtime complexities, but before that, I will be discussing about something called drop constant. So in our next video, I'll be talking about drop constant, like why it is required, okay, and why it is so important. So yes guys, this is all about from this video. Thank you so much for watching this video, and I'll see you next time.